NeurotechSF
Plus and upgrade to the Disney bundle for even more.
May 27, 2021, and I'm just going to do a super quick check to make sure that the YouTube
The following
channel has
is a conversation
audio.
with Brian Johnson,
This was
founder
an
of
issue
Kernel, a company
with,
that
my
has
Chrome
developed
tab being
devices
muted
that
by
can
default.
monitor
Made me
and
very
record
sad.
brain activity.
Oh yeah,
Previously,
we
he was the founder
have
of
that
Braintree,
audio.
a
Okay,
mobile
cool.
payment
So,
company
yeah, welcome
that
to
acquired
the
Venmo
NeurotechSF
and
Hack
then
Night
was
now
acquired
with
by
Sound
PayPal
Technology.
and eBay.
And
Quick mention of our
this
sponsors:
week we're going to be
for
looking
Sigmatic,
over the results from the
NetSuite,
spicy challenge that
Grammarly,
we
and
collected last week.
ExpressVPN. Check
Still
them out
working
in
on
the
a few
description
analysis
to
pieces,
support
so
this
it might be a
podcast.
little bit
As a
redundant
side
with
note,
what we
let me
did
say
last
that
week, but
this
I
was
think
a fun
it's
and
still worth
memorable
checking out.
experience, wearing
And
the
then,
Kernel Flow Brain interface
we'll
in the
also
beginning
do
of
a
this
little bit
conversation,
of looking
as you
to
can
see
see
if
if
we
you
can
watch
find
the
some
video
literature
version of this
of what
episode.
we should expect.
And
After all, we
there's a
have
Ubuntu
done our
Linux
preliminary
machine
analysis.
sitting next to
We're
me
still going to do a
collecting the
little
data
more
from my brain.
and make it
The whole
available
thing
in
gave me
notebooks,
hope
but
that the
we
mystery
can
of the human
start
mind
by
will be unlocked
looking to see
in the
can
coming
we find
decades,
an
as
equivalent,
we
or
begin
do
to
we
measure
see any
signals from the
information
brain
that
in a high
will
bandwidth
guide us
way.
into what we would
To understand the
expect to see,
mind, we either have to
the spicy
build it
food or the
or to
EEG
measure
and
it.
so on.
Both are worth a
In
try.
addition to that,
Thanks to
there's
Brian
some
and the
cool
rest of the Kernel
news
team for
in
making this little
the
demo happen.
neuroscience world. There's
This
a lot
is
of
the
things
Lex
going
Friedman
on,
podcast,
BCIs,
and here is my conversation
getting
with
data
Brian
that I think is
Johnson.
really going to change the
You ready, Lex?
profile
Yes, I'm
and the
ready.
scale of what we're doing.
Do you guys want to come in and put the interfaces on our heads? And then I will proceed to tell you a few jokes.
More people using
we
BCIs, having
we
access
have
to
two
BCIs,
incredible
interpreting
pieces
the
of
data,
technology and
self-collecting, and in
a machine
ways that are not
running
quite as
Ubuntu
terrible as
2004 in front of us.
what you folks
What
have
are
to
we
do
doing?
now.
All right, are these going on our heads?
They're going on our
It's been
heads,
a
yeah.
little while
And
since
they
we
will place
did
it
an
on our
introduction
heads
around,
for
and it's always nice
proper
when new
alignment.
folks show up. Now, right now, I think
Does this support
everybody's
giant heads?
cringing,
Because I kind of have a
or
giant
at least
head.
I hope they are.
Is this,
And
Is
don't
giant
worry,
head
there's
as
no
like an ego,
obligation
or are
to
you saying
introduce yourself,
physically?
but
Both.
we're always happy to have new folks, and we're always happy to know about what interests you, so that we can kind of like include that
nice
in
massage.
the conversation. So if you're feeling up to it, we'd love to know why anyone who's joining us for the first time
It's
is
okay to
joining
move
us
around.
tonight.
It feels,
and,
yeah.
even if you've been here before, what things interest you about it? That's cool as
This
well.
feels awesome.
Pretty good fit.
Thank you.
That feels good.
So this is big head friendly.
It suits you well, Lex.
Thank you.
I can go
I feel
first.
like I need to. I feel like
Hi
when I
guys,
wear this,
my
I need
name's
to sound like Sam
Minjun,
Harris,
and
calm,
I
collected.
recently, I have been
eloquent.
going to
I feel smarter,
NeuroHack
actually.
like
I don't think I've
meetups
ever felt
since like
quite as much like I'm
2019.
part of the future as now.
But
Have you ever worn a
after
brain interface
COVID,
or had your brain image?
I haven't been going to
never had my
the
brain imaged.
hackerspace,
The only way I've
the
analyzed my
noise
brain
bridge.
is
I mean,
by
and then that's how I met
talking to myself
Ben.
and thinking.
And
No direct data.
one
that is
day,
that is definitely
Morgan
a
just came
brain
to
interface.
our meeting, and he was
That has a
going
lot of
to like,
blind
talk about
spots.
this
I
group.
had some blind
So I was
spots,
like really
yeah.
interested about
Psychotherapy.
neuroscience and
That's right.
neurotech. So here
All right.
I am joining
Are
today.
we recording?
That's awesome! Wow, wonderful
All right.
timing, Minjun. So
So
just
Lex,
in case you haven't caught
the
some of the other
objective
episodes,
of this,
we've
I'm
been
going to
doing a spicy data collection
tell you
challenge
some
for
jokes.
May using
And your
consumer
objective is
BCIs.
to not smile.
So
as a
we're
Russian,
basically
you should have
Muses,
an edge.
BCIs,
Make the motherland proud.
Neurosity,
I gotcha.
and, soon, I
Okay.
think we're going to have a unicorn black as well.
Let's hear the jokes.
But yeah,
Lex,
we collected
and this
some
is
data.
from
we did
the Kernel
like
crew.
a baseline, the 5-minute collection.
We've been working on a device that can read your
had a few
mind,
volunteers
and we would love to see your
eat some
thoughts.
spicy food, and we tried to find a contrast. So we did
Is that the
actually
joke?
collect that, and it's been
That's
a
the
fun
opening.
project to kind of do something during the pandemic. Awesome that you're from Noisebridge. Were you part of the like Wednesdays
if I'm seeing the muscle
EG
activation
hack
correctly
nights?
on your
Yeah, I
lips,
was.
you're not going to do well.
That's
I've
awesome.
been
All right,
going there
here comes the first.
I'm screwed.
Here comes the
for
first
about
one.
a year.
Is this going to break the
and,
device?
Because of COVID, we
Is it,
just
is it
started doing
resilient
online
to,
meetings.
to laughter?
But I have got off track because I recently got
Lex,
into grad
what goes
school.
through a potato's brain?
So yeah, but here I am.
That's wonderful. Thank you so much for joining us. And,
I got already failed.
So,
That's the
hopefully
hilarious
we'll
opener.
we'll
Okay.
have content
What?
that's interesting for you.
Tater
But
thoughts.
no, that's wonderful. Thank you so much for joining.
Thank you for having me.
Yeah.
What kind of fish performs
All
brain
right.
surgery?
So and Jenny, you don't have to introduce
neural
yourself if
surgeon.
you don't want, but also oh yeah.
Hi,
Hi.
I have been here sort of on and off.
And so we're getting
usually
data
don't talk
of
because
everything
I
that's happening in
generally
my
have
brain
small
right now.
children in my background making a lot of noise, so it's hard to
activation
be heard,
patterns of your
so my
entire
name's Jenny
cortex.
Stenhouse. I'm
I'm
from
gonna try to do better.
New Zealand.
I'll edit out all the parts where I
And
laughed.
so
And Photoshop a serious face over them.
I kind of
You can recover.
tangentially got into
All right.
Neurotech
Lex,
because
what do scholars
I entered
eat
a random
when they're
competition
hungry?
with Neosensory.
I don't know
who make
what.
a haptic wristband.
Academia.
And
nuts.
then I asked them if I could be their like community manager or their developer advocate,
That was a
and
pretty
they
good
said
one.
yes. So I am now the developer
we'll do
advocate for
is- so you're wearing
Neosensory, helping run their competitions, and basically
Kernel Flow,
I love
which
that my job
is
description is helping other people
an
build
interface
cool
built
stuff and getting to
using
build some cool
technology
stuff
called
in
spectroscopy.
the
So it's
process
similar to
myself.
what we wear
And so sort
wearables
of
on the
through
wrist
that,
using
I've
light.
started exploring
So
other
using LiDAR,
neurotech
as you know.
stuff, and basically
And
I'm super curious.
We're using
and I love
that
listening
to image.
other,
It's a functional
to
imaging
smart
of
people
brain activity.
talk when
And
it's
so as your
totally outside
neurons
of my
fire
field. So
electrically and chemically,
background field.
it
So
creates
I have a very
blood
varied
oxygenation
background.
levels
I
when we're
have a
measuring
computer
that.
science
And so when
degree,
you'll see in the
and sort of went
reconstructions we do
into
for you,
game dev,
you'll see
and
your
then,
activation patterns in your brain as
a
throughout this
variety
entire
of
time we were
things
wearing
from
it. So in the
being a
reaction
tattoo
to the
artist
jokes and
to
as we were
chasing
sitting here
animals in
talking,
Africa with cameras
and so
and
it's
editing and all that kind of stuff.
we're moving towards
and then,
a real-time feed of
went
your
through
cortical
data
brain activity.
science
So there's a bunch of
stuff to
things that
finding
are in
voice. So I
contact
was
with
really
my
active in the voice industry for a
skull
while, and then
right now.
I
How many of
find
them are
myself
there?
here
And
with
so how many of them
desire
are?
to
What are
explore
they? What are the actual
sort of
sensors?
like how
There's
all those random
52
skills
modules.
can come together.
Each module
and
has
especially in this
one
really interesting
laser and
field of
6
BCI.
sensors.
That's really
And
great.
that's
The
wonderful
sensors
fire
to have you.
about
and,
100
thank you so much for
picoseconds.
joining us. I didn't
And
realize
then the photons
that you were,
scatter and
you were
absorb
sort
in
of
your brain.
the community
Then
representative.
a few
for
go in, a few
Neosensory.
come back out.
That's really
a bunch go in,
and
then a few come back out, and we
it seems like
sense
the future
those
for
photons,
BCIs
and then we
right now
do the
is so
reconstruction
bright,
of the
just in terms
activity.
of, the uptake
Overall,
and
there's about
interest, and,
1,000 plus
seems
channels
like a wonderful
that are sampling
place
your
to be,
activity.
helping people build cool
How
stuff.
difficult
with
is
this
it to make
particular
it as
technology.
comfortable as it is?
Yeah,
Is it
it's so
surprisingly
awesome. In fact,
comfortable?
someone is
I would not
building
think it would be comfortable.
BCI to the haptic
Something that's
wristband
measuring
in the current
brain
contest. So it'll be really
activity,
exciting to see how that goes.
I would not
and,
think it would be
I will
comfortable,
be sure
but
to
it
share
is.
when we have like
I
the
agree.
In
demo
fact, I'm going
day
to take
and
this home.
other stuff
Yeah,
coming
that's right.
through
So
from that.
people are
So
accustomed
I'm sure it might
to
pique some interest in this
being in
group
big
as well.
systems like fMRI,
Right.
where
Okay.
there's 120 decibels
So,
sounds,
hang
and you're
on
in
second. I
a
might have
claustrophobic
gotten
encasement,
a
or EEG, which is
copy
just
of
painful,
this
or
data.
surgery. And so, yes, I agree that this is a convenient option to be able to just put on your
All right,
head
so anyway, I'll take a
that
look
measures
at that
your brain
while we're
activity
doing other
in
stuff
the
so people don't have
contextual
to sit
environment
there
you
and wonder what
choose.
I'm
So if
talking
we
about.
want
Now,
to have it during a podcast, if we
super
want to be at
awesome.
home
And
in a business
Lisa,
setting,
if you were wondering
we-
what you walked into,
it's
we were
freedom to be
introducing
where
folks
to
that,
record your brain
joined us
activity in the
today.
setting that you
But you
choose.
don't,
Yeah, but
have
sort of
to
from an
say
engineering
hello or a
perspective,
little
are
bit about
these,
yourself, but if you are
what is it?
interested,
There's a
I'm
bunch
just
of
kinda
different
curious,
modular
what brought you
parts,
here,
and they're
what you're interested
kind of,
in with
there's like a
BCIs
rubber
and
band
how we
thing
can
where
make
they,
it
Sure.
they
Oh, you're
mold to the
back.
shape
Oh,
of your head.
Readers
That's right. So
Digest
we built
condensed
this
version, 'cause you
this
guys have
version of the
largely
mechanical
heard it
design
before.
to accommodate
But in case there's anybody
most
new,
adult heads.
So yeah, I'm just.
But I have a giant head, and
working
it
on a
fits
number of
fine.
different
It fits
projects,
well, actually. So
in a
I don't think I have an
VR,
average head.
And I'm also a new muse.
Okay, maybe I feel much better
disciple,
about my head now.
for lack
Maybe
of a
I'm
better word.
I'm more average than I
And
thought.
I'm really interested in.
Okay, so what
connecting
else
these
is
things
there
together with the
interesting you can say
visual
while it's
representation
on our heads? I can keep
tools
this
and
on the
stuff
whole
that we
time.
know
This is
develop
kind of
people
awesome.
out, and maybe I'll
And
make
it's
a
amazing
VR
for me as a fan of
exhibit that
Ubuntu. I use
mellows people
Ubuntu
out.
Mate. You guys should use
That's
that too.
awesome. Thank you
But
so much for
it's
joining us,
amazing
Lisa.
to
Yeah,
have
I'm
the
glad to
code
be
running
back.
Yeah.
to the side, measuring stuff and collecting data. I mean, I feel like much more important now that my data is being recorded.
Oh, it's always
Like
wonderful
somebody
when
you know when you
so great to
have a
see
good friend that
everyone.
listens
Okay,
to you,
let's
that actually like listens, like
Valeria is joining us
actually
from
is
very
listening
far
to you.
away
This
as
is what I
well.
feel
I
like,
believe the Ukraine.
like a much better
And,
friend
so
because it's like
we've got
accurately
quite the
listening to me.
coverage here. Okay, so
Ubuntu.
let's do
What
something
a
with it.
cool perspective. I hadn't thought about that.
All around the world.
Of
Cool. So
feeling
in
understood
terms of
Yeah.
the data
Heard.
collection,
Heard
we're going to take a
deeply
look a few minutes
by
at
the mechanical
data that we've
system
collected, and we're
that
also
is
going to look to
recording
see
your
if
brain
these
activity
comparisons are
versus the
working, so that we
human
can
that you're
I believe I've
engaging,
got a
that your
zip
mind immediately
where
goes
we can take a
to
peek, and it'll make the
that
contrast a little
there's this
easier to see than it
dimensionality and
was in the
depth of
last call.
understanding
But
of
what
this
I also
software
wanted
system, which you're
to
intimately
show
familiar
in
with.
general
And now you're able to
neuroscience
communicate communicate with this system in ways that you couldn't before.
There
I feel hurt.
I'm going to share my screen, and there's a podcast called
Yeah, I mean, I guess what's interesting about this is
podcast.
your intuitions
And
are.
if any of
You ready,
you
Lex?
roboticist, ethicist at MIT, a bunch of other stuff. Very, very, very knowledgeable, cool person. So Brian Johnson from Kernel came and gave him a demo of the Kernel Flow, and they were both wearing the device, and you get to see their brain activity. So for you wondering what is Kernel Flow, let's go take a look at it. So this is the very fancy functional near infrared spectroscopy device, and right here. And what that does is let you look at blood flow in the brain. And so here is the device from the bottom, and you can see all the electrodes, and using infrared light, they can measure which parts of your brain are receiving the most blood. And what that tells them is where activity is happening, because the more processing the brain is doing, the more blood that it will consume. So really interesting that, this method has been known for a very long time, but it was sort of infeasible in a consumer form factor, and really limited to the lab if you wanted to do it with any kind of density, although there were a few consumer devices that didn't really have a few electrodes, and you could do some very cool stuff. And then I think there's some combination devices coming that will have some good functionality. But this really is a big leap forward in terms of one device that you put on someone's head with lots and lots of resolution, different wavelengths, good sampling frequency, and so on. So yeah, here's an actual demo of it. You can obviously watch, Lex Friedman podcast number 186 yourself if you want to check it out. But I won't play the audio necessarily, and I certainly won't play the whole part. But I thought this little visualization of as Brian is asking Lex various questions, and you'll see in the podcast, some of the questions are straight up nonsensical to try to evoke sort of a thinking about it and trying to parse it. But yeah, you can see that, like, as he started speaking, there was a significant number of activations that you didn't see, and I think that's going to be very consistent. So if you're used to EEG, then you're used to sort of the data quality going badly when people are speaking. But also you can see that speaking has kind of like, right there. See, it uses a lot more activation than just sitting there. I think it's kind of fascinating. So yeah, if you've ever wondered, what does an FNIRS device look like? What do you see? Not all of them have this fancy topographical view, but you can make it from a device like this where you have good resolution information, but you can also just infer the blood flow of wherever you do have the electrode. So not all the FNIRS devices are going to be this sophisticated. They're not going to have this much resolution, but here you go. This is definitely on the way. And as much as this seems like an engineering design and very, a lot of work went into this, I'm sure, you can imagine that 5 years from now, we'll be marveling at how compact all these sensors are. Yes, that's a great question from Jenny. Absolutely. One of the nice things about this is that it's much less prone to movement artifacts. Now, I think there's going to be a caveat there, which is if you move around enough that the sensors lose contact in the sense of, like, physically jostling a lot, that I imagine would affect the signal quality or so on. But it's because it's not measuring electrical signals, it is not a problem if you're having muscle movements in your neck or your jaw or blinks or any of that. So it's really fascinating. FNIRS has some difficulties and trade-offs as well. So like every device, it's going to have some things that it doesn't deal with very gracefully. But yeah, what a cool idea to. I think one of the big things that people want to do with this, or certainly one things that I'm hoping for, is a very clear correlation between the EEG metrics of cognitive load and the near infrared metrics of cognitive load, because blood flow is such a good metric of cognitive load that, oh yeah, hold on, I have to turn on the annotations if I want the image. Okay, so they did that one as an annotation. All right, great.
Also, one thing is, isn't the kernel flow one of the devices where you can take out the individual FNIR sensor and put in an EEG sensor if you want?
I think that's the plan.
Yeah.
I don't know if they have it just yet, but I think they're certainly hoping to.
Yeah, but they showed the disassembly on their own YouTube channel of the actual sensor and how it's put together.
Oh, wow.
Yeah. Is it still on their YouTube? Let me check, because yeah, the that was a while ago. They might taken it down. It's a long. Oh no, it's still up, the teardown video. Let me share link to that. Yeah, kernel flow. Teardown.
I'll let the commercial play out. Yeah. Oh dear. Shakes fist. All right.
I know if I had a kernel flow device on, it would show a lot of anger. I don't know if anger.
You'd be spiking right now, and your valence would definitely be going negative. All right, I can understand that. All right, so here's the sensor. Right, this is great. Thanks for suggesting that, Ryan. Yeah, so it seems like you could swap these out with EEGs bit by bit, and that seems like it'd be phenomenal, because you would exactly be able to get those correlations. And yeah, really cool. So I'm very excited about, I mean, you know, kernel releasing this stuff into the market. I think that this is going to be a great addition. And I was just really impressed that, you know, here we are on the Lex Friedman podcast, 1 million subscribers. It's a pretty popular podcast for, you know, the scientific community and ethicists and so on. Some pretty famous guests, Sam Harris, etc. So it's just great. Like, here we go. 100,000 people have just seen a demo of a really nice BCI FNIRS device. That's definitely different from a few years ago. So I was very excited to see this kind of development. And yeah.
The best part of the teardown, I'd say right around 21 minutes, and you actually see the FNIRS sensor itself. Yeah, he shows the different layers of it, because it's multiple PCBs stacked on top of each other. So that's the actual like FNIRS, and then I think behind it is and I don't remember if it's that in the center is the actual emitter, and the 6 things around the edge are the collectors. But then there's a processing board, I think, on the piece behind it that also has that heat sink you can see on the big head strap. Oh, he's actually going to take it apart further. I forgot about this. But yeah, it's pretty cool and is very condensed of a chip.
Oh yeah, getting a camera to focus in space like that is a real pain. Not that I've ever tried. Yeah, it is really difficult. But yeah, look at that. This is all those little sensors. So I think it's really, really awesome that you know, we have this right now, and that these devices are just getting more and more popular. Okay, so Brian Johnson. Oh, inception moment. I will stop sharing the screen. Goodness, I apologize to anyone. All right, who is watching this on YouTube right now? I'm sure that was an exciting moment. Okay, cool. So I am going to grab the one second. Oh boy. All right. Let me start with going over the reports that we collected last week with the data. So I'm going to show the GitHub for Project Spicy, just so you kind of have an idea of what we're doing here. And then I'll show you the data that we've collected, and it's all in the repo. And then I'll show you the reports that we've got. So let's see here. I'm going to, nice. All right. So for the, goodness, GitHub, it's on github.com, NeurotechX, Project Spicy. So we have most of the basics covered, and the good stuff is in the protocol file. Now, this is the protocol for the Spicy collection. We had some other ones that we were doing for baselines, but that was just sort of for demonstration. This is the main protocol. So if you just click protocol.md, you'll be able to kind of follow the steps that we did for this experiment. A baseline of 5 minutes with eyes open or closed. When you've got that recorded, go ahead and record the Spicy experiment. And we suggested going through that in 2 ways. The first one was, great. The first one was have the Spicy item, start the recording halfway through. So those are the 2 that we did. So have the Spicy item, start the recording, less motor artifacts, better data, but we're not going to get as clear of a contrast, right? You're just comparing the baseline to the condition, and we won't necessarily see the onset. But the second time that you do the Spicy experiment, go ahead and do 2.5 minutes, then eat the spicy food, and that recording will be a bit noisier. There's going to be some muscle movement, as you're consuming the liquid or the spicy sauce, I believe in John's case. But you're going to get a recording that will show the contrast a little bit more clearly. In this case, we're standardizing on some naming conventions, so you kind of know what they look like. And also CSV is what we standardized on for this experiment. So if you look at the data, we've got Alex's data for Spicy, so that you're welcome to experiment with anytime. You've got my data of having fun on the call, and you're welcome to put it through whatever analysis pipeline you'd like. Then we've got John's data, and John also grabbed the baseline and the Spicy during recording, because those were the only ones that I think he was doing on the hack night. Then Daniel just recorded the previous set, which was some baselines, and that was still awesome because we can look at different people's brain data. And Melissa also recorded some brain data. One of the neat things about John and I submitting our data, all right, so let's go to, is that our brain data is quite different looking. So I'll show some example files, and I'll show, let's see here. Let's go Spicy during recording. Okay, now here is an example of what we see in the baseline, and here is an example of what we see in the experimental condition during the recording. So like the PSD changes, the alpha theta gets a bit more prominent. On the rear electrode, I have a pretty strong alpha peak. And so, this is what the data kind of looks like between the 2 conditions. But if we pull up John's data, you'll see that, his brain data is just a little bit different than mine. And as a result, not as alpha heavy, but definitely much more on the delta heavy. And I think this is a great example of what you're going to see when you're collecting data with consumer EEGs. It's just people have very, very, very different brain signals. And that can make it a little difficult to sort of compare. It can be difficult to know if you're getting valid readings. It can be difficult, you'll compare your data to sort of canonical examples. But some of these variations you'll probably get familiar with over time. And so I do think that this experiment has been really great from the sort of trying to understand, what different people responses are going to do, different hardware is going to look like, and so on. So in the analysis that we did last week, what we basically saw was that the alpha power tends to creep up a bit and the theta power tends to creep up a bit. The easiest way to quantify that was using the FOOF, which parameterizes the neural spectrum, a really cool GitHub tool released by Dr. Wojtek's lab out of UCSD. And so with this, you can sort of put some numerical values on the EEG data that you're seeing. So if we look at the difference of these two, here I had a 9.5 hertz alpha peak with a power of 1.07. Here I had an 8.8 hertz alpha peak with a power of 0.9. The bandwidth and here was 3.19, and here it was 2.23. So with this particular one, because of the way it fit, you'll see that the red line doesn't quite follow the data. So some of this stuff is a little bit inaccurate in terms of just comparing the you're going to have a little bit of variation into the quality of the fit, which is some of this metrics that you have here. But in this case, what we did see in the recordings was a slight shifting of the intensity of the band power. Like here was, we had kind of a baseline. But in the spicy during recording, you can definitely see delta activity, a bit of theta, and the alpha in the front didn't really change much, but the activity in the rear was kind of more noticeable. If you look at this is the pattern, you'll see that the beta levels go up, the gamma levels go up, theta kind of increases, alpha gets a little more intense, and there's a lot more delta. So there are changes, but as you can see, it's a little tricky to try to quantify these on these shorter recordings and in these particular conditions. So, okay, what kinds of analysis can we do? And also, how do we get a sense of what we're really looking for? Because we can pore over the data in a lot of detail, but and it's a good idea to do that. But at the same time, when we're dealing with a consumer device, there's sort of a limit to how much useful interpretation we're going to be able to do off any one recording or any one experiment or whatever. Obviously, you'll find some that come out better than others. So a very useful thing to do when you've done your initial analysis, you have some suspects. Okay, looks like, overall power levels go up. It looks like theta goes up. It looks like I see a lot more delta than I did previously. A good way to start the analysis is to sort of look around for publications and to see what they say. And have I put together a bunch that we can look at? No, of course not. But what we can do is Google around and see if we find anything. So we're looking for pain or spicy related literature. And most likely we're looking to see kind of what is the canonical definition of what we're expecting to see from pain. So let's see, pain response, EEG. Okay, does EEG drink? That's going to be a tricky one. That doesn't look like what we're looking for. Okay, brain rhythms of pain. Decoding of pain perception using EEG signals for prosthesis. Okay, so they want to impress us that they have a very nice classifier. And let's see if we can find the method of classification. All right, so spatiotemporal biomarkers. Hey, All right, so we see that during the stimulus, they show activity in CZ, P2, P4, P6. Now, okay, so each one of these channels is plotted as a separate row here. Let's see if I can zoom in a little to make this more clear. So these are the electrodes that they're talking about. There's CZ right in the center of the head. There's P2, P4, P6. And if you look at the labels on these recordings, you can see that this is CZ, P2, P4, P6. So, okay. The x-axis is in units of time, so this is time locked. And this is a spectrogram. So the colors represent the intensity, but you can see the scale on the right is plus 10 microvolts and minus 10 microvolts. So it actually seems like they're doing this off of raw. But yeah, with the locations that they selected, when applying the pain stimulus, they see a lot of activity in P2, P4, P6. And I'm wondering what the difference is between these EEG activity during the pre-stimulus. INO, MOD, and NOx stimulation. So they're doing 3 different stimulations, and it looks like the MOD one generated the strongest response. Okay, cool. So
it looks like the NOx also gave a strong response, but in the opposite.
Yeah, in the negative. You're right. You're right. Yeah, it caused a drop.
Almost it's a pretty close inversion to E. Like, if you even actually look at areas where there were almost no stimulus in E, those had a lot of negative stimulus in F. Like, it's actually freaky how much of a flip that is. Which so if that's in under a second, like, you can immediately see a difference, which in 0.2 of a second, no problem, which is pretty nice if that's some way you wanted to use some input, because that would be instantaneously identifiable. So I don't know if pain as a input method is used that great. Yeah. You want to click a button, feel pain every time you click a button.
Yeah, that I don't know. It seems like a pretty tough UI choice. I'm just kidding. But yeah, no, it is interesting how clear the contrast was. And you know what? Just for I found the comparison report, so we'll dig into that in a moment in terms of our data. And in the meantime, absolutely, you can see that this generates a pretty clear change. 10 microvolts is not a bonkers shift in voltage. Like in the case of the Muse, you're going to see oscillations of plus or minus 80 microvolts. So this is a pretty subtle shift. But at the same time, I think it definitely seems to show that there is a response there. And that, you know, in the mod example, the power increased, the raw power on the electrodes increased. And as Ryan pointed out on the NOx, it seems like an almost perfect inversion to where, you know, seems like, okay, there's 2 different ways that the brain can kind of respond to pain, at least from what I'm seeing here. Let's take a look at that NOx stimulation as well, just to get a little more detail. Oh, okay, so maybe that's, let's see, noxious stimulation. Let's find the description. Okay, cool. Innocuous, moderately intense, and noxious stimulation of an amputee's phantom hand through a transcutaneous nerve stimulation system. Okay, so this is actually going into the whole phantom limb continuous pain thing, which is another really interesting topic. People that have amputations sometimes experience the pain of the limb that was amputated. They feel like it's still there, and they feel that they don't have control over it. So a common scenario that I've heard described is that they feel like they're clenching their arm, and that they can't unclench it because it's not there. I mean, it sounds like a non sequitur, but that seems to be the experience. So this particular study is applying various stimuli to that. And the whole reason that you would do pain experiments with people that have phantom limb syndrome is that it can be quite painful. It's, try to imagine the sensation of tensing your arm for hours. That's what they experience, and not being able to release the muscles. So it seems quite horrible to consider that not only do you have the loss of the limb, but then you have this sort of continuous pain that you experience afterwards. And a lot of research goes into how to reduce that experienced pain. I believe there's a is it? No, I'm thinking of the wrong one. I'm mixing it. Lincoln's startup, but anyway, or is it Cura AR?
AR headset.
Is it?
Yeah.
Cura Tech. No.
Yeah, that's one of the.
That's the one. The other one. I'm sorry, I mixed those two together. Lincoln has one. Let me see if I can find. Karuna. I'm sorry. There it is. See, that's too many Ks. Karuna Therapeutics. Is this it? They might have gotten bought. This seems like a very... All right. I will. We'll get back into this, but there was a VR project to basically use VR to help people. It's called Karuna Labs. Okay, one last one.
Yeah, they didn't they come give a talk last year?
Yes.
Yes. Yeah.
Okay, so yeah, this is VR training. For exactly this virtual embodiment training. So that's basically that. Upper extremity, lumbar spine.
And I've been thinking about, I know some people who might be interested in testing this because using VR for this type of PT makes a lot of sense. And because I think right now they're using it up with mainly PT, but I can't remember if they talked about doing it with amputees in the future.
Yes, and that's the goal. The goal is, I believe that there are some treatments that currently use mirrors. So you bring a patient into a lab and you try to trick the brain into thinking the other arm is there by use of a mirror. And VR is sort of the next step up because you have this embodiment of an avatar, and really you're just trying to get the brain to sort of think that it has some control over that arm, so that you can start to manipulate it. Like maybe you could unclench it in VR, and then it would feel unclenched in real life. So it is fascinating to consider that, so many of these BCI uses have a direct and tangible application to something that really, really makes people's lives difficult. And it's wonderful to see these. So in this case, we're looking at the raw, and it looks like they saw some drops and increases based on the activity, and that this was very much time locked. So that it was based on sort of the stimulus response. Okay, so that doesn't look like it's going to give us power spectrum oscillation type things. Let's see if this does. This is fMRI. Neural oscillation, so I'm hoping EEG. All right, hang on a sec. Neuronal oscillations, yes. Hey, we have a figure. Let's see if we have another one. Nope, PSD was too much to... All right, so far I'm crapping out on the EEG articles. Let's try plan B, where we're going to look at the comparison plot that we pulled together so we can see the differences in these two conditions, and we can see whether that's giving us any insight. So to give you an idea of what we're comparing, it's baseline eyes open 2 and spicy during, I can't remember if I did recording or hack night, but I did one of the two. I know that's super useful. We'll take a peek in a moment, and I think I'll be able to figure it out which one it was. Okay. So I'm going to go ahead and unshare my data or my screen for a second, and then pull this up. Okay, this is just going swimming. Cool. I'll pull this up, and so in about 30 seconds, I'll reshare, and we will have that data up. Okay, and that works. Right, so I'm gonna extract that to desktop, and away we go. Cool, let me share the screen again. So what, in this case, what we're doing is we're comparing the, oh, sorry, did anyone have a question? All right, no problem. So what we're comparing is the data from the Spicy Hack Night Challenge. And as you can see, I've hacked together even more stuff. But let's take a look at this report. Oh, right, this is gonna be a mishmash. So yeah, I stitched together some very funny data between some stuff we did in an experiment previously, pupil data and so on. But let's look at this particular. So here we have the first recording. Here we have the second recording. All right. And here we have the TP9. So largely the same, except you can see that this one, because it was recorded probably during the hack night, it's got a lot more noise. The powers move around. This one's got a lot more beta, a lot more spiking too. But the thing that we were trying to do is we were trying to establish, like, how does the band power change? So in this one, we're doing the stimulus offset halfway through. And here, again, this is the stimulus. So we're seeing that the alpha goes up. We're seeing that beta goes up and the gamma goes up. So there are some changes, but it's pretty subtle, right? Let's see if we can quantify that another way. So we have these comparison reports, and this is just like a way that we can look at some of these. But let's try the lines, and I think the scatter is probably going to be a better choice. Okay, cool. So let's go for front alpha band power over time. And the blue recording is the control. And the orange recording is the experiment. So as we're calculating these data points, what I would say is, okay, these are 5-minute recordings of consumer devices. But what jumps out at me is that the blue, the control condition, stays in a rough range, but the orange one goes further. Okay, well, we were definitely introducing a stimulus. We were definitely doing the spicy food. We were hoping to see a contrast, and here's what we got. Okay. What about?
Do we have an image with like the like the either the mean or the median or something of the difference of them with like their overall like error margin, or is that too much to do with like a muse?
No,
Because
we can definitely do that. The thing is that because I ran into some problems with the timestamp formatting, I was thinking that we would be able to get more of this stuff working, but unfortunately, it was a little bit of a scramble just to kind of get these plots. So now that we have this, yes, if you were to look at one of the ones that works, like we have this plot for average number of pixels traversed per second. In this situation, you do get like R values and P values. The P is the confidence that you were talking about, and the R value is sort of the amount of change in the data.
Yeah, which is kind of noticeable, so that's pretty cool.
Right, and this is the
is
pixels traversed per second. Right, this is a unrelated measurement. It's not from this data, but we can try the lines as well. Let's go through. So let me just open all of them up. See, the problem is the lines didn't really draw, so I think we're stuck with that. Did the beta lines draw? No. Delta, negative. All right, cool. So we're gonna live with the scatter plots for now. And let's also see if the violin plots worked. Front, mean, alpha. Hey, okay, so this worked. Cool. So if you want to look at the two time series side by side, in the control condition, the power of alpha is down here. This is the mean value for the whole set for each sample. And then here is the mean value for the experimental condition. So, okay, kind of cool. You can see the change. The beta is a big shift upward, right, more noticeable than the alpha. The delta is also a big shift upward. Like in the control, the power was typically around 1. Here it's spread quite a bit higher. And then if we look at the rears, the rear alpha higher in the experiment. So instead of being kind of range bound from 3 to 7, it goes all the way up to 25. Some of that is definitely like noise, but some of that is going to be valid. The beta really shot up in the rear as well. And the delta shot up quite a bit. So, would I publish these results? Probably not. If I was using a consumer device to do a pilot study to tell me, do I think that I can detect anything with this? I would say, yeah, right? I mean, I would say, okay, let's do a more controlled experiment. Let's figure out the units of Scoville that we're introducing to people. Let's see what's going on. But yeah, I think it's definitely the case that you can say that there's something there, but the interpretation gets a little hazy. So let's just go through the fronts. We'll do all the bands. And then when we're done with that, we'll do the rears. And we'll see kind of like what our initial conclusions are. All right. So in terms of alpha power, it's nice to see that the two recordings kind of track together at the start. I think it's a great sign. And then they diverge, which is what you want to see when you apply your stimulus. Now, some of this initial stuff might be motor movement, could also be the onset because I wasn't sort of keeping the cayenne pepper in my mouth the whole time. But it does look like there was a pretty clear change in the orange recording compared to the blue recording. The blue recording stayed below 1. The orange recording had a lot of spikes above that, and it was right around the time of the administration. So if you look at the time elapsed, we did the stimulus at 2.5 minutes. So here this is at the 2-minute mark, and there you go. Okay, so the front mean beta is interesting. In the second recording, we have a shift from the baseline. So the baseline's all at 1. And this is all right around 2.5. That's pretty sure that I'm doing the one during the hack night. So overall, I'm kind of like more stressed out. But all the same, even when you have a shift like this, what I don't see is a spike in the blues when there's a stimulus onset, but I still see one in the oranges. So sure, there's, the baseline is not identical, yet I feel like there is a beta response here that shows us something that we didn't see in the control condition. What about the delta? Well, again, right, we're starting to see a consistent pattern. Here the delta is higher, but there's interesting activity around the 2.5 mark. It really does seem quite different than our control condition. Gamma, surprisingly, the exact same story. Higher values, but a spike in the middle that is completely absent in the blue data. And theta has some, see, this one looks a little bit unreliable to me because we've got stuff before the stimulus, we've got stuff after the stimulus. The pattern isn't very tight. So personally, I'm not sure that I trust this plot. But again, we see more activity, more variation. A little bit before the stimulus, which we wouldn't expect, but still pretty good. Okay. And just to give you an idea, if we were comparing baseline to the one where they did it before, then you would expect to see this kind of like broad spectrum shift. But if you're comparing the baseline to the one where they're doing the spicy during, it would be nice to see the baseline and the spicy during track together like this. That's a good sign. And then to see a deviation. That's also a good sign. Okay, so any question about these plots, and then we can take a look at the rears. By the way, thank you all for bearing with me. Today was a little bit disorganized, but I really wanted to try to show some of this stuff if I could. Okay, great. We don't have any questions on these plots. Let's take a look at the rear channels. Sorry, this is some, we're gonna go back to mean, yeah. Yeah, we calculated a few different ways, so we can check those if you prefer. And theta. Okay, so what do we got? The alpha shows very similar to the fronts. The powers are higher because of the Muse arrangement of electrodes. But once again, we've got a tracking for the first 2 minutes, slight increase here, a little bit of divergence. Stimulus onset happens here. And then it seems like the orange is a little elevated compared to the blue, at least compared to what was the case before. All right. So what are we seeing in the beta? Well, geez, beta looks quite different. Shows a higher and climbing amount of load. Maybe this is me sort of dreading the upcoming spicy experience that I'm going to have, a sort of anticipatory rise. There is some interesting stuff with beta in terms of inhibition, motor inhibition, and so on. But still, if we're comparing these two, then there's a jump. This might be bad data. This might be, the stimulus onset. But here we go. Now the beta settles into a higher baseline. This is very interesting to see, to me, because again, we're trying to induce a change with this manipulation. To me, this looks like a decent change. Okay, rear delta. More of some initial spiking, then a recovery, and then kind of a divergence. A little different than the other ones, but still follows the same pattern as most of the other electrodes do. Gamma, higher than the baseline, stimulus onset, doubles in value for the remainder of the reporting. Pretty cool to see a shift that big. And then the rear theta, once again, the theta doesn't really seem to tell a story, just kind of there. You could say that it's centered on 4 to 5, and that, these dots seem pretty evenly distributed. I don't see a huge pattern here. It doesn't seem like it was very, very significant. So, yeah, in these sets of plots, I do think that we see the stimulus onset. I think that the delta, sorry, let's go back. The alpha has some interesting activity, but doesn't show a huge contrast. The beta seems to show a consistent story and a significant shift. The delta definitely seems to have some differences, especially frontal, but I think the rear does as well. And the gamma had some interesting changes. So I'm just going to open up a notepad. So for Alex, increases in delta, beta, gamma, very marginal. Beta seems equivalent. Alpha shows an increase, but not as dramatic as the others. So yeah, these are basically the conclusions that I draw from this particular experiment. And I think it's reasonable to say that much like that paper showed in terms of the raw, I'm going to turn this off for a sec and bring up the paper. As much as it wasn't super informative in terms of doing the PSD, which is how we're kind of doing the comparison, I still think that this shows, you know, a shift in signaling. And so, okay, you know, I would describe, you know, what I was doing was fairly moderate. I don't know what their definition of moderate is. I hope it isn't horrific, but yeah. So for the level of spice that we did to try not to induce sweating, I think we see a shift that's commensurate with sort of this broadband type of thing. If we look at the GitHub in John's data, I think he had like a Jupyter notebook, which I'm guessing is probably not gonna. I don't think I have IPython installed on my system. But yeah, if you look at John's plots, awesome. We do get to see them. Here are, do we have the updated ones for the spicy, non-spicy? These are the previous set. Okay. So this is John's data from his eyes open, eyes closed, YouTube, and art experiments. And this just kind of gives you another representation of what it's like when you kind of stack these together. So you'll see that as you look at the PSD in the eyes closed, John's power spectrum is this shallower type of curve, but it has a lot more power across the beta, alpha, beta range. When he's reading the article, the Medium article that we were just looking at, his delta is quite high. But then like at this point, compared to the eyes closed, the theta is significantly below, the alpha is significantly below, and so on. And this is what you would expect consistent with someone, you know, just sitting there. So if you look at the eyes open condition, it ends up being a very close analog to, you know, the article, except the article has much more gamma activity. And the YouTube link is sort of a broad spectrum increase, but sorry, hit the wrong mouse button. Let's cool. Reload this. Great. So yeah, you can see that these responses are pretty subtle, but sometimes you get this overall shift upwards. And in this case for John, it was in the eyes closed condition. In this case for me, it seems that applying spicy food to my tongue also generates a broad spectrum shift upwards. Okay, so we took a look at the data from last week. We took a look at the comparison report real quick that we had on the spicy data. I'm happy to try to open up a few more EEG links, see if we get lucky there. But any questions so far on the data that we collected, the notebooks, the analysis, or maybe even the interpretation of the plots that we looked at today? Did that seem straightforward to everybody, or were there any questions about like some of the details?
I have one question.
Sure.
So we have spicy food recording, right? And how do we choose with which baseline we should compare it with?
Excellent. Okay, great question. So the two baselines are meant to be kind of like an extra layer of redundancy. I think one might be better than the other, but the way that I would suggest starting on how to pick one is looking at the power over time. So I believe that in the first, the 05, 20, 2021 Alex baseline eyes open, this is sort of the first baseline that I did, and I was getting a few Slack notifications in the middle of it. So I'm trying to have as little activity as possible. But the reason that, I didn't feel so hot about this recording is you can see it takes me about 2 minutes to kind of relax. And then this part is different. So I don't get very excited about a baseline that is so dissimilar. On the rears, it's closer. But even here, you have all this theta activity that kind of settles down. So I felt like my particular baseline one wasn't great. So right after I recorded it, if you look here, the values go up to like 1 and drop down to 0.6. And right after I recorded it, I tried to do another one where I didn't have the phone open. I wasn't receiving any, messages, and I was already kind of like calm because I'd been sitting there for 5 minutes for the previous baseline. So my suggestion is, if you want a slightly cleaner baseline, I think baseline eyes open 2 should work. But both of them should probably be all right. It's just that I think this one is slightly more representative of the baseline.
Thanks. But what about YouTube baseline? It's more for fun.
Yeah, we didn't. Let's see. Do I have so the YouTube wasn't baseline based. That was, and I can process that one real quick if you want. Let's populate it and. Excellent. So go ahead and save. And oh, I think I have this. Come on. I was pretty sure I had this rolling. Nope. But of course, I was messing around with it. Come on. So there's something. Oh, yeah. Hold on. Let me try this one more time as admin. I was having some strange issues with that. Give me a second to open up Spider. All right. Again, the joys and the perils of hacking 30 seconds before the call. Sometimes I enable or disable certain modules to make things run properly. And yeah, I have a feeling that that went badly. Uno momento. Okay, so
it's okay. I just want to understand the purpose of having these two not baseline recordings we did 2 weeks ago.
Oh, okay, yeah. It was an attempt to show stimuli that I didn't think would generate a very good contrast. And so it's not a baseline, but it's an activity that I think is going to give you pretty minimal response. So you could use the YouTube video as a comparison for the spicy food, and you could use the article as a comparison for the spicy food. So it was more like I didn't see the purpose of having 4 baselines. So it was kind of like 2 baselines and 2 quasi baselines is maybe a good way to describe it.
Okay, great. I got it.
Cool. Thank you. Yeah, and I'll get the reports running, and I think we had them on Drive. But anyway, I'll take a peek at those as well. Okay, so that's it. Now, let's take a look at, can we find, oh boy, yes, there we go. So this was the one that I think Jaden had read. Okay, so EEG-based bioassay for preclinical testing. Yeah, so this is how well do painkillers work. Pregabalin. Okay, they picked 3 of them, and they picked the optimal, and they're talking about chronic pains. Earlier studies suggested that resting state EEG oscillations in the theta band are enhanced in neurogenic pain patients and attenuated after therapeutic thalamic lesions. Okay, a series of studies, we showed that the oscillations within the low frequency theta are enhanced using pain and EEG. Pain-induced theta power is reversed upon spontaneous resolution of pain and attenuated following administration of analgesics. Furthermore, a causal relationship between pain-induced theta power, sensory behavior, and microscopic unitary activity in the thalamus. So, what do they say happens to the theta power? Okay. Let's look at chart D. Time-dependent increases. Representative examples from C. Okay, here we go. Here's our PSD. So these are some pretty subtle changes. Okay, they found that in this condition, the theta power changed from 4.5 to 4.6 resting state. And yeah, since representative examples of EEG naive and CCI conditions the same rat. Well, anyway, I don't see the shift in the, there we go. Okay. Man. Okay, so charts aside, their particular claim is that as the pain increases, the theta should go up. As the pain decreases, the theta should go down. And they really target the theta band. A lot of this could have to do with the power of using clinical EEG instead of consumer EEG. The resolution, signal quality of the electrodes are going to be very high. The other thing is the locations that you're doing. The muse is frontal and temporal parietal. So it could be that the locations that we can sample with the consumer hardware are not represented. But what I would say is in our data, I didn't see that very clearly because I did see increases in delta, beta, gamma. Saw a little bit of an increase in alpha, and it was theta that was the worst one. Let's go back and take a look one more time at the comparison, right? So we'll pull up the raw reports to look at the band power over time without the subsampling. I'll explain to you what I mean by that. But and okay. So here we go. Front. Now these are slightly different electrodes, so maybe this is a little unrepresentative, but in this case, I guess there's a theta increase here. It's pretty subtle, but I think that was pre-stimulus. See, this really didn't seem like a huge shift in either. This is the baseline and this is the experiment. But on the rears, I think there is a little more activity. In the baseline, everything is really quiet. There's a little bit of alpha increase, but you've got mostly flat. Here, there's definitely more. The theta I'm suspicious of because of the timing of the offset kind of doesn't align with anything else. So I guess in my particular experiment, I didn't replicate the results. But then again, this was one attempt with completely different hardware and different electrode locations. Oh, sorry. Question? Okay. And I do see a change in the alpha. I do see a change in the delta. And I honestly think that the beta is the most interesting to me. That's just me. Because beta is kind of fatigue inhibition related. So I can definitely see delta being along for the ride. I can see alpha being along for the ride. But from the experiments that I've done, I find the beta shift interesting. Now, obviously, there isn't a paper that says that they see the beta shifts. The paper says theta, but we didn't see the theta. Also, the gamma came out pretty well. And you see the vertical alignment, the consistency with which these show is nice because that kind of indicates an overall shift similar to John's data with the notebook, where you have a broadband shift in the condition. So the alpha is a lot higher, the beta is a lot higher, and so on. But yeah, that's so in this case, our very, very, very experimental results don't seem to line up exactly with that one paper, but this is one subject and one test. So this is basically what we're trying to in detail conclude from this data, which is, where do we see these changes and are they consistent? So what I can tell you is for next week, I will definitely get a couple of these comparisons going, which, doesn't help us now, I know. But what I'll do is I'll have plots like this for John's data, and I'll have plots like this for my data. Like I said, I figured it would be a simple cut and paste just like the other stuff, but because the files that we're doing for that are slightly different, Excel was doing this really gnarly stuff with mangling the files, and that was no bueno. So we were just getting a lot of Python errors because the timestamp was in scientific notation and we were expecting, the normal stuff. So it takes a little doing to correct. But yeah, this is the result of that. This is what we're expecting to see. So if we look at that report where we also have the comparisons, right, we'll just sort of say, there's really no difference in the plots between the sum and the mean, but I'll go ahead and just show you that they're basically equivalent. Right, we need to do the scatter because... So you might be wondering what exactly is the difference. I mean, I'm sure you're familiar with the difference between mean and median mathematically. When you're talking about analyzing data, most of the time your medians will look pretty similar, but in some cases they will be clipped off. So here it doesn't look like there's any shifts. But if you're plotting peaks, if you're plotting certain things that are very transient events, sometimes median will kind of cut off the extremes. But most of the time, median is a great one to use because it's fairly robust and so on. So let's just pull up these plots one more time: beta, delta, gamma, and theta. So again, these are the same data, kind of different views, right? In one, we have 5 lines on the same chart. But like I said, alpha stays the same and then has this deviation. It's not super significant. The beta does show a very nice clear pattern, and compared to where it was, there's a solid increase of about 50%. Delta showed a lot of variations, but we had some spiking and some increases above the baseline with the stimulus onset. And the gamma also showed some decent changes, right? Higher than the baseline. It's not great when the baseline and the whatever differ so much, but definitely the difference between doing a recording live on a hack night versus the baseline. Show you some differences. The theta, I mean, I don't know, if we consider the literature and we consider how subtle their changes were, if we ignore the fact that we're seeing the onset earlier than we expect, let's say we try to ascribe that to, something, thinking about something, anticipation, whatever, there's still an increase from the beginning. I don't know. I would like to see a cleaner contrast before I would say, yeah, we agree with what the paper said. So just unfortunate that in this one experiment, but that's the thing. When you're collecting pilot data, this is a 5-minute investment. So if you do 3 baselines, and you don't like how they look, you're off 15 minutes. It's no big deal. If you do 3, sample collections like this, you can see whether they're consistent or not. And that's why we did it kind of twice, to see if the data is the same. And we'll take a look at the rear medians using the new info that we have. Delta, gamma, theta. Okay, and once again, alpha seems to increase 50% or so. This is all below 10. We have a lot of data points that's at 15 microvolts of power for that bin for those 3 seconds. Here we see a pretty clear shift in the beta. See, I really like how this came out because this is a nice
Alex,
pattern.
are you sharing your screen?
Have I been talking this entire time with no screen? Yes, I have.
Yeah.
Thank you, Ryan. That's terrible. I apologize.
You stopped sharing a little while ago. Probably about 3-4 minutes ago, maybe.
That's horrible. I'm very sorry, and thank you so much for saying something, Ryan. Oh, boy. Okay. So this is the beta that I was talking about that really kind of shows us a nice contrast. You have this slow building above the baseline. You have the onset, and then you settle into a new range. This is almost twice the value that it was previously, from 15 microvolts in the beta range to 25 microvolts in the beta range. And that's, given the subtleness of what we saw in the paper, 10 microvolts on the raw, pretty subtle on the PSD in terms of resting theta changes. I think this is fairly consistent, but what we didn't see was a strong shift in the theta. So the delta has this kind of initial spike, drops back down, and then over here it's above the baseline. The gamma seems to look a lot like the beta, which is very promising, that you've got this trend that's sitting here, the shift, and then the higher values. But the theta, again, didn't, especially in the rear, didn't really come through. So there you have it for our initial data analysis, some of which you spent looking at me talking. And what I think I conclude from this is that, yeah, we are seeing shifts. This is an experiment worth replicating. I wouldn't say that we're narrowing down the theta response, so that part doesn't quite jive. But I'll stop sharing. But definitely we're doing something much more significant than the whole eyes open YouTube or the eyes open article. So now we have a little bit of comparisons that we can triangulate between. The baselines give us resting state, no stimulus. The slight manipulations of YouTube and article give us a little bit of variation. And then the spicy should give us a good amount of variation. So as you're doing your analysis, that's what I think you're hoping to see with our particular data. Okay, so Ryan, we can go ahead and stop the recording. I think we're good on the analysis today, and then I think we can brief.
I want to discuss the.
Oh, please, yes. Go right ahead.
The stuff on stream.
Yes, so, before we cut the recording. So take it away. Sir.
I'll start sharing my screen. And talk about like what I found that got published or not really published yesterday, but probably leaked. This is a new photo of the OpenBCI Gallia headset that a well-known VR YouTube influencer press person published yesterday around 6 p.m. I'm pretty sure it's a leak since reverse image searching this image won't bring up anything from OpenBCI, and I actually haven't seen any other news like VR news group share this image yet. But yeah, so this is the OpenBCI Gallia in one of its prototype forms, as you can see by it having things like zip ties on it and what looks like open battery or some sort of PCB board with like film covering it or something in the back. As we talked about before the meeting, this layout, which is 6 rear electrodes, 2 top electrodes, is extremely similar to the Neurable VR headset, which has a similar, very similar electrode layout, but only 7 electrodes. This never really was released, other than in I think a couple dev kits. But yeah, so another piece that's interesting. See, this is the first time we've seen any of the faceplate stuff. Which, for those who don't know, the OpenBCI Gallia headset isn't just the EG head strap portion. It is also a version of the Physio HMD faceplate. This is an old version on a HoloLens. Yeah, here's some older versions. So this is one of the developers at OpenBCI who's worked on hardware. And this is what the old faceplate looked like. You can kind of see the faceplate here, which looks like it's the same one as this, just maybe some newer foam padding layout, but it has different holes that look like they might either be going to be pogo pins or soft rubber electrodes, sensor pads. Yeah, you can ooh, okay, I can't zoom really. Yeah, there's yeah, let's see. So this is the old image they showed. So this integrates with the Index headset. And for those interested in like some of the different sensors it's going to have, a lot the EOG and which is mainly eye tracking stuff, that is going to be by Tobii eye tracking. The EMG, EDA, temp, and heart rate sensor, which I think is a PPG sensor, those are all going to be on the face plate. And then DEG is the head strap. These are going to be pretty interesting once they come out. We're still not sure of